All right, so let's resume the chapter at which where we left in the last lecture. We were discussing the configurations of a single pin as a GPIO. So as far as the configurations are concerned, we discussed a flow chart. Let us switch to the flow chart directly. This was the flow chart of enabling a single pin or more than one pins at a single port. So when in the very first step, we were initializing or we were enabling the peripheral clocks for a port. So there were 6 different ports, and each port can be enabled or disabled via a single bit inside a RCGC GPIO register. There was a special register at a special address, and in that register, each bit was representing each port. So by enabling or disabling a port means by setting or resetting a single bit inside that register. For example, bit 0 was representing the port A clock enability. Similarly, bit 1 was representing the port B enability. And keep on going onwards, we can say the bit 6 will represent the port F enability. So we will enable the port by setting a particular set of bits inside our register RCGC GPIO register. Then we will take a decision whether you want to make a GPIO as a default GPIO or you want to assign an alternate functionality to it. If you want to assign any alternate functionality, in that case, there was a register called AFSEL register, alternate function selection register. For that register, each bit was representing each pin of the port. So for each pin, we have a flexibility to choose whether the pin will behave as a default GPIO or it will behave as an alternate functionality. So if we reset that particular bit, it means we are enabling the pin as a default GPIO. If we set that particular bit, it means we are in alternate functionality. And among those alternate functionalities, different peripheral devices are multiplexed to that particular pin via some hardware tools. So there was a special register called port control register. That port control register was selecting one of those peripheral devices through which that will be multiplexed to that pin, and that pin will start behaving that peripheral transmitter or receiver. If you are not in your alternate function, you are in your default GPIO functionality, then the next decision would be if you want to make it digitally enabled or not. So if you want to turn on as a digital pin, then in that case, there was a special register called DEN register. So inside the DEN register, once again, each bit in DEN register represents each pin on a port. So if you want to set any particular pin as a digital pin, then you have to set that particular bit inside that register. So after making it digitally enabled, you will set the direction of it. 1 means you are selecting as an output, 0 means you are selecting it as an input. So if you want to turn on it as an input device, then you will take the pad control settings, whether you want to put that pin as a pull up configured pin or pull down configured pin, or what would be the current sourcing or current syncing ability of that pin. And if you want to turn it on as a default output pin, then in that case, you have to select what would be the current sourcing ability of it, whether you want to connect it as an open drain pin or what would be the slew rate. So these are the settings of configuring a single GPIO. And after discussing the base addresses and the mapping of the registers, we were going to start. This was a concept which we discussed last time as well. This was called the register masking for write and read for the data register. For the data register, which is used to fetch the data if the pin is behaving as an input, and which is also used to drive the pin if the pin is behaving as an output. So that data register can have a flexibility of adding offset to it. Whatever offset in the address that you will add inside that data register's address, that address can be coded like this in these 10 bits. And starting from bit 2 till bit 9, you can say each bit of that address pin is representing the is controlling the masking or unmasking ability of GPIO data register. For example, if you want to write something onto the data register, the offset that you have added is 0A4. So 0A4's representation will look like this. The 1 will represent that particular bit will be unmasked. 0 represents that particular bit will be masked. So if you want to mask that bit, it means you will set 0 over here, and whatever data that you will write at this particular bit, that will not be transferred to that register. So that will take its own previous value. And if you will put 1 inside the address of that particular bit, in that case, you are unmasking that bit and you can write or read from that pin simultaneously. So this was the concept which in the last lecture, which is register masking, that is developed by TIVA boards only. Now let's look at the example. In this particular example, we are going to configure port F. For port F, the default functionality of the port F is port F PF1 is connected to a red LED, the PF2 is connected to a blue LED, and PF3 is connected to a green LED. And PF0 is connected to switch 2, and PF1 is connected to switch 1. This is the main functions of the port F, and it has a few sensors, which is LEDs, and a few input devices, which are switches connected directly to it. Our goal is to enable any of these LEDs. So if we want to enable any of these LEDs, it simply means we are setting PF3 or PF2 or PF1 as an output device, which is digital in nature. So that will be configured as digital output device that will be controlling the value, that will be controlling the LED. So in order to configure it, first of all, we will enable the clock for that GPIO port. After that, we will reset the alternate functionality selection register because we do not want it as an alternate function. We just want its default functionality of GPIO. Then we will set the direction of it as a digital output function. This will be chosen by two registers. The first register, DEN register, will make it digitally enabled, and the DIR direction register will make it a output as an output pin. So two registers will be configured to control the direction of that pin and to set it as a digital pin. And then we will do the pad settings. So this is a complete code. We will not cover the assembly version of it. You can see that assembly version yourself. Let's discuss the C code directly. And for this C code, for the simplicity, let's copy the whole code onto Keel directly so that we could see it in a little. Just give me a second. All right, so can you see the window of Keel?
Yes,
Okay, thank you. Okay, so starting from the start, these are a few macros. We will not declare variables that will be pointing to some specific registers. We will start with macros because the macros are the one that will not take any memory. So the first macro is the system clock RCGC GPIO register. You can rename this register as well, but I have taken it as a default value, as a default name that is written in your data sheet as well. So system control RCGC GPIO. This will be controlling the clock that is coming to the port directly. And its address is 0x. In hexa, its address is 400FE608. So this is the base address of this particular register. And here I have written its data type. Its data type is volatile in nature. Why it is declared as volatile? Can somebody tell what is the difference between volatile variable and a simple variable? We covered this concept in lab 2. इससे anyone
में एक टाइप को कंपाइलर ऑप्टिमाइज नहीं कर सकता, उसकी गारंटी है कि ये चेंज नहीं होगा। अब वो कौन सा
जी,
होता है
बिल्कुल।
मुझे, लेकिन
जब आप किसी वेरिएबल को वोलेटाइल डिक्लेयर करते हैं तो इट मींस यू आर आस्किंग द कंपाइलर कि अगर ये अनएक्सपेक्टेडली भी चेंज हो जाए, यानी किसी सेंसर के थ्रू या किसी और डेटा वेरिएबल के थ्रू ये अनएक्सपेक्टेडली कोड के अगेंस्ट भी अगर चेंज हो जाए तो उससे घबराना नहीं है। सो इट मींस कि ये कंपाइलर इस वेरिएबल को मजीद ऑप्टिमाइज नहीं करेगा, इसकी कोई वैल्यू हार्ड कोडेड नहीं रखेगा और ये एक्सपेक्ट करेगा कि ये वेरिएबल कभी भी चेंज हो सकता है। So volatile variable is the one that can change its state unexpectedly at any time because it is connected to some external world sensor. So it's a volatile in nature variable that will be unsigned long type. So unsigned means it will have an unsigned numbers to it, only positive numbers, and long means it will have a capacity of a long variable. And there are two pointer values. Those pointer values are actually declaring that we are pointing to the address of this variable, address to this register, and we are accessing the data of it. So it is a pointer that is pointing to that address, and then we are controlling the data of that address. So these two statics means this is a pointer to the address, and this static represents this is pointing to the data of that pointer. So we are actually controlling the data of a pointer that is pointing to that address. So this is a double pointer concept. So by calling this macro, we can directly access the data that is associated at this particular address. So we are pointing a macro to a specific address to control its data parameter. In the next line, there is the same line, but this time we have GPIO port F. We are controlling port F now. And inside the GPIO port F, we have a data register that previously had the offset of 0. But now in this case, we have added an offset of 3FC. Now, why we have added this 3FC? Because if we will add 3FC inside the data register, that will unmask each and every bit. If we will add 3FC offset in the data register, that will unmask each and every bit of that port. So we want to unmask every bit of that register. That is why we have added 3FC in the data register. Otherwise, its default value was all zeros. So 3FC at the LSP side has been added to just unmask all the bits of the data register. So 3FC is the data register's offset. Then the direction register, port F direction register. Its name in the datasheet is GPIO port F direction register. So in the direction register, we should know the base address. Base address of port F is 40025000. And at where I have seen this address can be seen in, let me open the data sheet for you now. Okay, so this is the data sheet of the TIVA board, and inside the data sheet, chapter 10 was associated to GPIOs. And in this chapter, we discussed the base addresses of all the ports. So these are the base addresses of each ports. So we should first of all know the base address. This is the base address of port F, 40025000 in hex. So APB bus is being connected to port F and has a base address of 40025000. And after knowing the base address of each port, we must know the offset value of each register. And that offset value is given over here. The direction register, GPIO direction register, has an offset of 400. So we will take the base address of port F, we will add this offset to it, and we can access the GPIO direction register. So this is the same thing we have done over here as well. This was the base address 40025000, and we have added 400 to it. So by adding 400 offset to that base address, we can access the direction register. So direction register's address for port F would be 40025400. And this has been computed through datasheet. Next comes the digital enable register. Now, if we will switch to the datasheet again, we can see the digital enable register has an offset of DEN register. This is the DEN register. So GPIO DEN register has an offset of 51C. So 51C will be added to the base address of that particular port, जिस port का DEN register access करना है. So we will add this offset 51C in the base address of port F, and we can access the DEN register of port F. So this is the same thing we have done over here. 40025400. That was the base address of port F. We added 51C inside it, and getting an offset of 51C, now we can access the digital enable register. So we only need these three registers for the time being. We will not access the AFSEL register because its default value is 0. So we will not change that default value. So we only need, for the sake of optimization, we need only the data register, we need the direction register, we need the digital enable register. Now, in order to turn on the clock for port F, next question arises that which value should be added in that register to turn on the clock for port F. If we will go back to the data sheet once again, in fact, data sheet se ke bajaye we will discuss it over here. Let's say we have this RCGC register over here, which has the first 6 bits available to you over here. Each bit was controlling each port. So this bit is associated to, let's suppose, port A. This bit is associated to, let's suppose, port B. This bit is associated to port C. This bit is associated to port D. Same is the case here, port E, and this one is reserved for port F. Let's suppose this is the data map or the register map of RCGC GPIO register. So if I will name it as, this is system controlled RCGC GPIO register. And this is the registered map of its first 6 bits, starting from bit 0 to bit 5. Now the question is, which value should be added inside? Which value should be added inside these bits so that port F's clock will get enabled? By setting a bit means we are enabling the clock. By resetting the bits means we are disabling the clock. So at first we do not want to enable port A, so we will put 0 over here. So port A will be in sleep mode or in hibernate mode, and we will not enable the clock for it. We do not want to use port B as well, so that is why it will be 0 as well. We do not want port C, we do not want port D, port E will be disabled as well, but we want to set port F clocks. So in that case, we will put 1 over here. The bit that is assigned to port F, that will be set. And the number that is in binary notation over here, it can be converted into hexadecimal notation as well. And in hexa, you can say the first 4 bits, these 4 bits are representing 0. And the next 2 bits are representing 2. So in hexa, you can say by adding 0x20 inside this particular register, we can set the clock for port F. So this register will be given a value of 0x20. So this is the way you can turn on the clock for port F. Let's suppose if I say that we need a few pins of port F and we need a few pins of port B as well. So what should be the value that will be assigned to this particular register so that my port B and port F get enabled? Can somebody answer it?
सर बी और एफ को करना है
जी, बी और एफ को करना है।
तो हो जाएगा।
यहाँ पर भी आप 1 पुट कर देंगे, so you will put 1 over here. It means this number in hexa will become 2 and this number in hexa is also 2. So we can associate 2 in this register so that we can enable port B as well as port F. Similarly, if you want to turn on any combination of these ports, you want a few pins of port D, we want few pins of port F, we want few pins of port A, you can adjust any combination inside these bits and you can turn on all the associated ports that you need. So this is the way of using RCGC GPIO register. Now in our case, in this example, we are only assigning a few, we are only using a few pins of port F. So we only want to enable the port F clock. So that is why we have declared a macro over here. And this macro's name is GPIO port F clock enable. If you want to define that macro, you can define it. Otherwise, just put a hard-coded value of 20 inside this register. So this 0x20 is a number that will be assigned to this RCGC GPIO register to turn on the clock for port F. And in the next case, let's say we want to enable pin 3. So if we want to enable the pin 3, this is the register map of direction register. This is the GPIO direction register, and this is the register map of it. It's starting from bit 0 to bit 7. These are the bits which are readable as well as writable. All other bits are reserved for the future purposes. So we cannot access all other bits. We can only access the first 8 bits of it. And in the first 8 bits, each bit is representing the each pin of the port. So each pin can be controlled by setting or resetting associated bit inside this register. For example, if I want to turn on the PF3 as my output pin, I will put 1 over here. Similarly, if I want to turn on the bit PF2, then in that case, I will put 1 over here as well. So by adjusting the values of these direction bits, we can associate the directions to a GPIO port pins at a क्या कह रहा था मैं पता नहीं. So by setting or resetting the bits and a combination of bits in this direction register, we can set the input or output functionality of any GPIO port pin. So 0 means the corresponding pin will behave as an input. 1 means corresponding pin will behave as an output. So in our case, let's suppose we only need the PF3 pin. So for PF3, what should be the value that should be assigned to this particular register? We want PF3.
08.
If we want to PF3 pin as an output, it means I will put 1 over here. So 1 will be at this point, zeros will be all over these registers, and the corresponding hexadecimal number that will be coming out of these binaries notation, that will be 8. The first 4 bits are representing 8. Next 4 bits are representing 0. Let me check if I have the pen access over here. Pen. So I will put 1 over here. I will put 0 over here. I will put 0 over here as well. Similarly, 0 at this point, 0 at this point, and zeros all over it. So it means these 4 pins, these 4 bits are representing 8. And all other bits are representing 0. So if I will put 08 in hexa inside this register, I will be controlling my PF3. If in case I want to turn on my PF2 as well as my PF1 as well, in that case, I will put any combination of bits inside this register, and I can control the direction of each pin at PF port F level. So coming back to the code again, this is the number 08 that will be enabling the pin 3 of the port F if this number will be put inside the direction register as well as the digital enable register. So we will put this value inside the digital enable register as well, just by to enable PF3 as an digital pin. And we will put the same number inside the direction register as well by turning it as an output pin. And if these macros are reserved for the data register, so let's suppose these are defined as 8, 8 again, and this is the delay macro. Inside the main function, there is my variable, volatile unsigned long variable, that is a dummy variable on which I will run a loop. This is another variable a equals 0, just dummy initialization. This is the line system clock RCGC GPIO register is being given a value of port F clock enable, and port F clock enables values was 0x20. So 0x20 has been assigned to this particular register, so to turn on the clock for port F. And after turning on the clock, I have taken a dummy assignment just to waste a few clock cycles. So I have taken an assignment operation in the next line just to waste a few operations so that this particular value is being set inside the register and the clock will become smooth. So this is a dummy assignment just to waste a few clock cycles. In the next line, in the direction register of port F, I have put in this macro, and this macro's value is 0x08. So by adjusting the value in 0x08 over here, we can control the direction as well as the digital enability of PF3 pin. So in the next two lines, we are controlling the direction of the PF3 and we are making the PF3 as a digitally enabled pin. Next is a forever loop.
इज इक्वल टू के साथ साइन कौन सा है असाइनमेंट में
हाँ ये अच्छा है, ये साइन जो है दिस साइन इज एन ऑड सिंबल. ऑड सिंबल इसलिए यूज किया जाता है बिकॉज इफ देयर वाज any previous values assigned to direction register as well as digital enable register, we will not permanently overwrite it. Let's suppose the PF3 register had previously the direction register had previously a value 1 1 and all zeros, and we want to turn on this PF3 bit as well. In that case, we will take the previous value of the direction register. We will take an OR with 0x08. By taking OR operation, the previous values will remain preserved and the 1 will be added at a particular bit at which we want to add it. So in that case, the previous value will remain preserved. So it is a good practice in embedded programming to always use OR equal. Do not overwrite the previous value of it. For example, let's suppose RCGC GPIO register was already controlling the the clocks of port A and port B. And now we also want to add the functionality inside the port F as well. In that case, we will take the previous value of it and we will take an OR with the new value. So by taking OR means all other previous bits will be reserved and the value at which we will put 1 at a particular bit, that will be set only. So this is not a forced assignment or overtaking assignment. It is preserving its previous value as well. If we simply use equal sign, it means this is the forced assignment and we are updating we are overwriting the previous value by a totally new value. Now next line is a forever loop. This forever loop will keep on iterating till forever. And this is the data register. I am putting something inside the data register. And what is this something? This macro is LED on. LED on is over here, 0x08. So I will put 1 inside PF3 data bit. So the data bit that is controlling my PF3, that will be given a value 1. So I will put 1 over here. I will wait for a few clock cycles just for the smooth operation. And this is a for loop. This for loop is just adding a delay. It is not doing anything. It is terminated by semicolon. It means it's an empty loop. It will keep on waiting until the UL loop will keep iterating itself until the value delay is reached. And what is this value delay? Delay value is over here. It is 200,000. So 200,000 clock cycles will be wasted over here. Then in the next line, I am turning off that bit and I am waiting again. So in this particular example, my data register will turn on the LED. It will wait for a few seconds or few clock cycles and then it will turn it off. And LED will keep on toggling itself because it's a forever loop. So it's a simple LED toggling program. In this program, we are toggling an LED, we are turning it on, we are waiting for a few clock cycles, few 100,000 clock cycles, and then we are turning it off. We are once again waiting for a few hundred clock cycles. So this is a wave inside this while one loop, inside this forever loop, there is a toggling of LED happening at a fixed rate, which is controlled by this delay variable. And let's suppose if you want to debug it, if we want to see that the code is working or not, then in that case, we will go to the debugger session. Okay, just give me a second. So here we are now inside the main function. Now if we want to see that इसकी आपको जरूरत नहीं है अभी इसकी चलिए आने दें इसको. Anyways, we want to see the registers of a few GPIO ports. So in order to see that those registers, we will go to the view tab. Inside the view tab, this is the system viewer button. Inside the system viewer, these are the all ports, or sorry, all peripherals that are assigned to our TIVA board. And inside those ports, this is the GPIO port F. So if we will click on GPIO port F, all the registers of port F will be available in the debugger session. We can see if those values which we want to update are getting updated or not. In the very first line, we are going to update the clock for port F. So if we will execute it, sorry, we were on top of the program. We are initializing a few variables. Then we are updating the clock for port F. So clock of port F has got updated. Then a dummy assignment. This dummy assignment will help you to see if the value is assigned directly or not. So this is the dummy assignment. Then GPIO port F direction register. We will go to the direction register. We will update its value. So if I will execute it, you can see over here.
Excuse me, sir.
G.
Sir, bottom left corner पे access violation error आ रहा.
जी एक्सेस वायलेशन एरर आ रहा है. मैंने एक्चुअली कुछ सेटिंग्स चेंज की हुई हैं इसकी टीवा बोर्ड के हिसाब से, इसलिए डिबगर ये चल नहीं रहा. मैं इसका लॉजिक एनालाइजर ऑन करके बैठा हुआ था. So anyways, you can do it yourself. You can you can start the debugger session. You can go to the specific line and you can see if the register getting updated or not. In your case, your direction register will get updated by a value that is assigned to it over here. So this direction register will get updated after the execution of this line. Similarly, digital enable register will get updated. Digital enable register is over here. In the next line, this value will get updated and keep on going onwards. We can see if the configurations are correct or not. So these are all the registers of port F. So this was the first example in which we were trying to configure a single pin as a GPIO digital output. And in that case, we accessed only PF3. Now let's switch to the next example. This is the complete code of it. This was the complete code of it. I have changed a few macros name, so don't get confused with it. This is RCGC GPIO register. This is my port F data register, direction register, digital enable register, and inside the main function, there was a forever loop that was toggling the pin 3. So pin 3 was getting toggled again and again, and that pin 3 is connected to green LED. So if we will burn that code onto our actual real TIVA board, the green LED will start toggling. Okay, the next concept is called the input interfacing for the switch. Coming back to our block diagram, the PF3 pin was connected to two switches which are associated at PF4 and PF0, and three output LEDs which are connected to PF1, PF2, and PF3. In the next example, we are going to discuss how we can configure a single pin as an input digital pin, and we can access the switch that is connected to PF0 or PF4. Now, the software program for the switch interfacing can be implemented using two different methods. In the first method is called polling based method. Second is called interrupt based method. Interrupt based method will be discussed in the next chapter. For the time being, we will discuss the polling based method. Now, polling based means we will keep on iterating a loop on the value of a switch, that if it is 1 or 0, we will keep on asking it at every clock cycle that if it is 0 or not. So we will just keep on polling at a single pin that what is its data, what is this data, what is this data. So we'll keep on iterating in a single loop that what is the value of it, and we will keep on waiting until the switch is pressed or it is unpressed. So this is the method called polling based. in interrupt based, we will not keep a check on the data register of that particular switch. An interrupt will automatically occur. The processor will keep on doing its normal task, and interrupt will arrive whenever the switch will be pressed. So in that case, that method is called the interrupt based method. The switch will automatically generate an interrupt. The processor will simply go to its handler and will perform the task which was assigned on the switch press. So this is an efficient way of implementing a input interfacing, which is interrupt based interfacing. Rather than keep on calling itself and keep on doing nothing, just keep a check on that particular flag variable. Now the next concept, which is a very important concept in the hardware embedded programming, is called the switch debouncing or simple switch bouncing. The switch that is connected to a microcontroller, it has a spring that is just behind that particular button. So just beside that button, there is a specific spring that has its own momentum and its elasticity. So if we will put a microscope or CRO, an oscilloscope at that particular pin at which the switch is connected, and we will try to press it once. So if we will try to press it once, that elasticity stored inside the spring will generate a pulsating electric signal. This is a pulsating electric signal that is coming out of the switch if we will press the switch only once. In ideal notation, the switch should go to a high state or any low state. It depends on if the switch is connected as a pull-up notation or as a pull-down configuration. It should toggle its stage only once, and it should come back to its original value once again once the switch is unpressed. But in real scenario, it will change its state once, then it will keep on changing itself unless the elasticity that is stored inside the spring connected with that button, it will dissipate all its energy. So if we will configure a single switch as an input, and if we will press that switch only once, it will not generate the interrupt only one time. It will keep on generating the interrupts and it will keep on changing its state. It will keep on calling the handler inside it till the elastic energy stored in the string will be damped out. So in this case, we have to configure some switch debouncing program with your hardware so that it should avoid these debouncing or the bouncing errors. So this is called debouncing error or simple bouncing errors. So it will result a pulsating electric signal instead of a clean transition. And if you are using a microcontroller GPIO pin configured as an input, the switch debouncing can be interpreted as multiple switch press. We are pressing the switch at a very high frequency. So it will generate an
सर माइक्रोकंट्रोलर्स के जो इनपुट्स होते हैं ये स्विचेस वाले, ये पहले से श्मिट ट्रिगर्ड नहीं हुए होते हैं?
नहीं पहले से नहीं हुए होते। अगर हुए भी हो ना तो भी इसके अंदर डिबाउंसिंग एरर आ जाता है क्योंकि वो पोजीशन खराब हो जाती है कभी कभार स्प्रिंग की। तो उस वजह से आपको सॉफ्टवेयर में डिजिटली भी कुछ ना कुछ ऐड करना पड़ता है, कुछ डिले ऐड करना पड़ता है जिससे कि आप ये जो डिबाउंसिंग का एरर है ना ये रिमूव कर सकें। तो उसके लिए कुछ नहीं करना होता, बस एक लूप चलानी होती है कुछ देर के लिए, एक एम्प्टी लूप, ताकि वो डिले ऐड कर दे।
सर ये वाली चीज आर्किटेक्चर में कवर नहीं होती क्योंकि हमने लास्ट डीएसटी कोर्स में
आर्किटेक्चर में ये चीज कवर नहीं होती। बाज़ औक़ात ये होता है जैसे आप अगर FPGAs यूज कर रहे हैं ना, तो FPGAs के केस में आपके पास जो स्विच लगा हुआ है ना, वो स्विच वो प्रेस वाला स्विच नहीं है, उसमें आपके पास वो बाई स्टेट स्विच है, ऊपर वो 0 हो रहा है, नीचे वो 1 हो रहा है। तो अगर वो स्विच यूज कर रहे हैं उसमें मसला नहीं होता। लेकिन जो आपके माइक्रो कंट्रोलर में यहाँ लगा हुआ है ना टीवा में, अगर मैं स्विच की आपको शेप दिखाऊं तो ये स्विच जो है ना ये आपके पास कुछ इस फॉर्म में है। आप इसको प्रेस करेंगे तो ये 1 हो जाएगा, अनप्रेस करेंगे 0 हो जाएगा, या इट डिपेंड्स इफ इट इज कनेक्टेड एज अ पुल अप और पुल डाउन कॉन्फ़िगरेशन। सो ये इस तरह का स्विच है, इसके नीचे स्प्रिंग लगा हुआ जो इसको वापस लेके आता है अपनी स्टेट पे। तो जब भी इस तरह का कोई स्विच आप यूज करेंगे इसमें डिबाउंसिंग आएगी।
यस सर, पुश बटन का ही हमने वो बनाया था, जो आर्किटेक्चर डिजाइन किया था जिसके अंदर उसकी बाउंसिंग को वो ऑप्टिमाइज कर देता था। जो आर्किटेक्चर का जो
किया जा सकता है, आपने हार्डवेयर लेवल पे भी किया जा सकता है, लेकिन जस्ट फॉर द सेक ऑफ क्लैरिटी हम इसको सॉफ्टवेयर में भी इजीली इंप्लीमेंट कर देते हैं। ये एरर आहिस्ता आहिस्ता खत्म होता जा रहा है बिकॉज जब हम लोग इसको इंप्लीमेंट करते हैं तो साथ ही एक इसमें ट्रिगर भी लगा देते हैं, फिल्टर भी लगा देते हैं। तो वो फिल्टर जो है वो उसकी एब्रप्ट चेंज को अवॉइड कर देते हैं। जैसे इन दिस केस दिस इज द हार्डवेयर सॉल्यूशन ऑफ अवॉइडिंग द डिबाउंसिंग। दिस इज अ पोर्ट पिन This is the switch connected to it. This is the pull-up resistor, which is connected with VCC and the ground. And this is the capacitor over it. This capacitor will avoid that high frequency ripple. So ये वो high frequency ripple जो produce होंगे उनको filter out कर देगा. So it will act as a low pass filter, and it will reduce all the high frequency noises and all the high frequency ripples associated to it. So this is a very basic hardware level solution of avoiding that debouncing. And in this, in the case, let's suppose if this circuitry is not connected at the architecture level, then there is a software solution as well. That software solution is just adding a delay. Add a delay once the switch is pressed, start a loop, and that loop will do nothing. That will just avoid the debouncing and the debouncing intervals, and it will keep on adding a delay till this debouncing sequence will reach its maximum value. So the switch is detected as pressed. A delay corresponding to switch debouncing interval, it will be calculated by hit and trial, is inserted, and the switch is checked again for being pressed. If the switch is detected as pressed again, we declare the switch is pressed. So this is a software solution of adding a delay of an interval that is calculated by hit and trial, and that interval is called switch debouncing interval. So we will keep on waiting till this interval is passed out, and then we will check the state of the switch again. So this is the way of adding a debouncing solution in your program. Okay, at the flowchart level, if we want to turn on a switch, then in that case, we first of all have to enable the clock for GPIO port. That switch is, let's say, connected to PF4. So we want to configure the PF4 as our digital input pin. So for the first part, we have to enable the clock for GPIO port. Then we will reset AFSCL value because we do not want it as an alternate functionality. We will configure the GPIO pin as a digital input pin. So digital input pin will be assigned as by setting a bit in digital enable register and by resetting the bit in the direction register, because in the direction register 0 was representing input, 1 was representing output. So we will put some value in the digital enable register to make it digital pin, and then we will reset a value in the direction register to make it as an input pin. And then we will do the pad control setting, and we will put a restriction whether you want to use it at a pull up configuration or as a pull down configuration. In the case of pull up configuration, this is called pull up configuration. In the case of pull up configuration, if the switch is unpressed, it means all the voltage will appear over here, no current will flow through it, and that will give you a logic high value. And in the case when switch is pressed, it will become short circuited and the current will be flown, all voltage will be across resistor, and we will get a logic 0 over here. So 0 means switch is pressed, 1 means switch is unpressed. But in the case of other way around, if the voltage across the resistor is our output and we have connected this switch as a pull down configuration mode, in that case 0 means the switch is unpressed, and 1 means switch will be pressed. So in the case of pull up configuration or pull down configuration, the switching sequence will depend on the value or the voltage across the resistor. So we will do the pad control setting and we will put the switch as a pull up configuration mode. So in pull up configuration mode, we will put digital input condition on that switch pin. We will reset AFSCL. We will turn on the clock. These will be the configuration steps to configure a single pin as an input pin. And this is the whole code of it. RCGC GPIO register, once again, same discussion. The data register, the direction register, digital enable register, pull up register. Pull up register has the offset of 510. So we have added 510 offset in the base address of port F. And here are two different data registers. For the first data register, it is called RD data read register. In this case, I have added the offset in the base address such that I have only unmasked my PF4 pin. So by adding offset of 040 inside the data register, I have unmasked only PF4. And in the case of data write register, I have unmasked only PF3. So I have unmasked only PF3 if I want to write something in the data register, and I have unmasked only PF4 if I want to read something from the register, so that I will get only the state of switch and I will only control the state of the LED. So whenever switch will be pressed, the LED will be toggled. So a read register will give me the input data that is coming from the switch to the data register, and write register will give me the access to control the state of the LED. And inside the main function, a flag variable is defined. RCGC GPIO register is configured with the number that will enable the port F clock, and that number is same as that of previous one, which is 0x20. So 0x20 has been put inside RCGC register to turn on the clock for port F. Direction digital enable register has been given a value of 0x20 plus 0x40 that will turn on PF4 as well as PF3 as a digital pin. And inside the direction register, I am putting 0x80 inside the direction register to just turn on PF3 as an output. PF4 will start behaving as an input automatically. And pull up register is configuring the PF4 as a pull up mode. And inside the while loop, I have declared a condition that if my switch is pressed, it means it will give me a 0. So if my switch is pressed, my data read register will give me a 0. I will add a loop delay of some delay debounce interval value. This delay function is just doing nothing. It is just adding. This is the body of the delay function. It is doing just nothing. It will assign a local variable and it will keep on iterating a empty for loop till this counter is reached. So it's just a delay function that is adding a delay of few clock cycles. If the flag is 0 and the switch is pressed, I will toggle the LED. I will update the flag. Otherwise, in the next iteration, I will just update the flag again. So in the first iteration, the clock will be enabled. In the second iteration, when the switch will be pressed again, the LED will be disabled because it's an XOR operation. So XOR operation is used to toggle the LEDs. If there would be 1 in the previous iteration, there will be 0 in the next iteration. So XOR will keep on toggling the bits of PF3 and the LED will keep on toggling itself once the switch is pressed or unpressed. So this is how a single pin can be used as an input interface, or as other pin of the same port can be used as an output interface. Is this thing clear?
Yes, sir.
Okay, great. So far we have only interfaced, we have only configured a single pin as an output or a single pin as an input. Now in this case, now we are configuring multiple pins at the same time, and we want to control a 7-segment display. As you already know from your DSD course, a 7-segment display basically has 7 different pins assigned to it as a data pin. So this is the data pin that is controlling A, B, C, D, E, F, G segments. And each data pin can be given some value to put some LEDs on and put some LEDs off and to generate the numerical digits. So 7-segment display is one of the widely used displays that can display decimal and hexadecimal, and in some cases a few special characters that can be mapped with these 7 segments. Each of these 7-segmented display is called a segment. This is called a segment. And it will have a control or cathode pin that will be controlling if this 7-segment is enabled or not. This controlling strategy can be of 2 types. A 7-segment can be of common cathode type. A 7-segment can be of common anode type. In the case of common cathode, we will put ground or 0 volts at the control bit. This control bit will become 0 if you want to enable 7-segment, and this control bit will become 1 if we want to disable this cathode this 7-segment. And if it is connected to ground or 0, if the control data pin that LED will start glowing. So if I want to turn on a LED segment, then I will put 1 over here and that LED segment will start glowing. Similarly, if we want to turn on A and B simultaneously, I will put 1 over here. So this is a way of controlling a 7-segment display which is connected as a common cathode terminal. So common cathode terminal means selection will be active low and this will be high. If we put 1, it means it is on. If we will put 0, it means it is off. So it is called active high configuration and the controlling sequence will be active low. In the other way around, in common anode terminals, in case of common anode, the anode will be connected at a common point, and that will be the controlling bit, and that controlling bit will be 1 if we want to enable the 7 segment, and this will be 0 if we want to disable it. So if it is connected with a high logic high value, in that case, if I will put 0 at any other combination of A, B, C, D, E, F, G, that LED will start glowing. So in this case, my segment selection will be active high and my data selection will be active low. So my data will be active low in nature. My segment selection will be active high in nature. So there are two different 7-segment displays that are available in the market. These are common cathode type and common anode type. This is the brief introduction of those. We have already covered this introduction. And the next concept is time multiplexing. You already know from the DSD lab. In the time multiplex data, we will have a number of 7 segments that are connected in parallel. Their data bits will be common, and those data bits will provide the data to each and every 7 segment. And based on the segment selection bits, we will choose which segment should get enabled and which segment should get disabled. And we will keep on popping one segment at one time, and we will keep on multiplexing it at a very high rate so that human eye will see that all the 7 segments are glowing and each of them are giving some different inputs. So in the time multiplex data, each 7-segment element is driven individually at a time because data bus is common. But due to persistence of VN, it appears to the viewer that the entire display is continuously active because we will do this time multiplexing at a very high frequency. So due to the persistence of the VN, the viewer will keep on assuming that it is actively displaying the numbers continuously. If every segment is interfaced separately to the microcontroller, then the number of GPIOs required will be 8N or 7N. If we associate the dot bit also, then for the data bus, we need 8N, where N is the number of 7 segments, or in the best case, it will be 7N. If there are 4 7 segments, we have to use 28 different data pins just to control 4 7 segments. And we have only the capacity of 43 pins. So सारे pins इसी में लग जाएंगे. So for N is equal to 4, the number of GPIO pins required for individually separate segment connections are 28. While we require only 11 in the case of time multiplexing. Why? Because 7 will be assigned as a data bus, 4 will be assigned as a segment selection, and those 4 will be doing the time multiplexing thing just to making or enabling or disabling one segment at one time, and all other 7 bits will be providing the data to each segment simultaneously. So this is called the time multiplex data. It should be realized that for every time multiplex display, each segment is only activated for 1 over n time, where n is the number of clock cycles or the fraction of the clock cycle on which you want to refresh the whole 7 segment. So 1 over n time fraction of the total display refresh clock cycle duration. And to avoid any flickering, the refresh frequency should be approximately 50 Hz in practice, or larger than 50 Hz. So this is the configuration on which you want to code your microcontroller. Your port A pins, 4 pins are chosen from port A. Those will be controlling the segment selection part. So time multiplexing and the segment selection will be done using port A. And port B's pins are chosen to control the data of these 7 segments. So these datas will be connected directly to port B, and those 7 segment selection will be connected to port A. So port A will be controlling the segment selection, port B will be controlling the data sequences, and we want to control the port A and port B simultaneously. So in terms of hierarchical steps, the flowchart of the configuration would be: we will turn on the clock for port A, we will turn on the clock for port B, we will set the direction of port A 4 pins as an output pin, and we will make them digital. So port A's 4 pins will behave as a digital output pins. Similarly, port B's 7 pins will behave as digital output pins. So we will configure 7 pins of port B as digital output. We will configure 4 pins of port A as digital output, and we will keep on doing the time multiplexing thing in your main code to avoid the flickering and to give different value as 7 segment. This is the code of it. We have once again RCGC register. Now in this case, we need 2 different ports. So in that case, we want 2 different data registers. We want 2 different direction registers. We have 2 different digital enable registers. So port A's base address is 4000 4000, and 3FC is being added to it. 3FC means I want to unmask every bit. In the case of port B, my base address is 4000 5000. So 3FC is added in as an offset data register because I want to unmask every bit of port B as well. And in the case of port F, I only need a switch. So that is why I have put 040. I only need one LED. So in the case of one LED, I have added 040 offset inside the base address of port F. In the case of direction register, offset was 400. So 400 added as in the base address of port A, in the base address of port B, and in the base address, sorry, there is no port F. Similarly, in the digital enable register, in the digital enable register, offset was 51C. So 51C offset is added for in the base address of port A. 51C is added in the base address of port B, and 51C is added in the base address of port F. And pull up configuration means I'm supposed to use a port F pull up register which had an offset of 510. So 510 offset added in the base address of port F. So these are the macros assigned with the addresses of the registers. I want to turn on my port A, port B, and port F. So the number that I will put inside my RCGC register, that will be 23. Why is it 23? If I will go to the Word file again, I want to turn on port F, I want to turn on port B, I want to turn on port A as well. So this will be 1. So looking at these numbers, this is representing my hexadecimal 3, and this is representing my hexadecimal 2. So 23 will be put inside this RCGC GPIO register to turn on the clock for port A, port B, and port F. So 23 is the number that will be put inside this register to turn on the clock for port A, B, and F. Port A pins. The port A pins which are chosen for the segment selection are port A2, port A3, and port A4 and 5. So PA2, PA3, PA4, and 5 that will be used as a segment selection pins. And those 7 segment selection pins will be put as a digital output pins. So if we want to turn on, if I will erase it, eraser hota hai isme. All right, so I want to turn on PA2, I want to turn on PA3, I want to turn on PA4, I want to turn on PA5, and rest of the bits should be 0. So this is 0, this is 0, this is 0, and this is 0 as well. So the corresponding number that will be put inside my port A direction register and port A digital enable register would be, if we will convert this number in hexa, this will be 1100, which is, what is 1100? Who is on right? 1100 is C. And this 0011 is basically 3. So we will put 3C inside port A direction register to turn on PA2, 3, 4, and 5 as my output pins. So this 3C is coming from that point of view. This is the flashing frequency. This is the digit refresh frequency. This is the debouncing error, a debouncing frequency. So these are the macros that are defined as a debouncing errors as well as the refreshing errors. First, we will do the port initialization. Forget about these arrays for the time being. These arrays are mapping the 7-segment display values. Whatever value that you want to display on the 7-segment, that is encoded as a hexadecimal value. So this hexadecimal value C0 will be put over here. So C0 will generate some sort of A, B, C, D, E, F, G configuration, and we will display something on the 7-segment. So this is just a number that is printing, I guess, double E something. So that is a number that is printing some value. In fact, this is printing some sort of digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is printing some digits on the 7-segment. First comes the port initialization. Where is the port initialization? Let's look at the port initialization first. This is the port initialization function. In this port initialization, I have put a value 0x23 inside my RCGC register. So inside my RCGC register, I have put 23, which is turning on the clock for port A, port B, and port F. So 3 ports are getting configured at the same time. Then port B direction register. Port B direction register has been put inside FF. FF means I am using my whole port B. So complete port B, 8 pins of the port B will be used as an output pins. Similarly, FF has been put inside digital enable register because I want to turn on all the bits as a digital pins. In the case of port A, I only need 4 pins, and those 4 pins were generating a macro of 3C. So 3C will be put inside direction register, and the same number will be put inside digital enable register. So these 4 lines are actually configuring the whole port B as my digital output pins and 4 pins of port A as digital output. And port F is connected to switch. So switch will be configured as a digital input pin, and it will be configured as pull up configuration. So pull up configured digital input button that will be used as an input to my system. Data register will be configured as all ones, and the data register of port B will be configured as all ones, because if I will put 1 1 everywhere, it means I will turn off all the segments. So all the segments will be turned off. So these are the initialization steps. We will initialize the clock, we will initialize the direction and digital enability, and then we will put something in the data register to turn off all the system. So I have turned off all LEDs. After the port initialization, inside my main function, there is a while loop, forever loop. It is scanning the switch. Scanning the switch means I am checking if the switch is 0 or not. So scan switch is once again a function which is written over here. This is the same function that we have discussed in the previous example as well. So scan switch, count variable, flag variable 0. If the switch is pressed, it means I am in this for if condition. Inside the if condition, I am adding a delay to some debouncing. If the flag is 0 and my port F data register is also 0, I am updating my counter. And if my counter exceeds 99999, I will update the count. And by doing so, I am actually selecting my array segments inside the 7 segment. So tetra 9 means 0 will flash 1 at the first time. Sorry, 1 will flash 1 at the 7 segment, 2 will flash 2 at the 7 segment, 3 will flash 3 at the 7 segment, and we will keep on iterating unless 9999 is put at the 7 segments. So 4 segments will show you 9999. After that, it will give you a 0. So starting from all zeros, we will keep on toggling the numbers on the 7 segment, and that will be telling you how many times the switch is being pressed. So at every one press of the switch, the 7 segment will get updated to 1. So starting from all zeros, at the first iteration will be updated to 1, then it will update to 2, then 3, 4, up to 9999. So it is actually counting how many times the switch is getting pressed. And this function binary to BCD decoder is just like a decoder that will take the current value of count, and that will decide at which segment which number should be displayed. So in this function, I am actually getting this binary value. The fourth segment, that will be my 1000th value. That 1000th value will be put at the fourth segment divided by 1000. We have subtracted this value because now we want to compute the 100th value. For 100th value, I am dividing it by 100. Then for the 10th value, I am dividing it by 10. And for the LSB, I am just taking the value which is remaining. So in this way, my BCD value 3 will give me the digit that will be showing at the 7th segment when we have a specific count value. BCD value 1 will be controlling the 10th digit, BCD value 0 will be controlling the 0th digit, and BCD value 3 will be controlling the 1000th digit. And this is a simple delay loop. So inside the main function, I will scan the switch. Based on the value of the count, I will check the get the BCD value, which is the global variable, which is getting controlled by the switch selection and the BCD to 7 segment decoder. We will get some array value. We will put it at the 7 segment display. Similarly, we will keep on toggling the port A pins so that we keep on multiplexing them, and we will keep on adding the delay that will keep on refreshing the 7 segments. So this is the whole code of 7 segment display. This whole code is a part of your lab number 8, and the switch selection and the LED interfacing was a part of your lab 7. But since there is no hardware given to you so far, but I don't know how this lab will be carried out. So this was the code of your lab number 8. This was the code of your lab 7, the switch one and the interfacing one, LED interfacing. So LED interfacing and switch interfacing was a part of your lab 7, and BCD 7 segment display was a part of your lab 8. So we will not cover the key pair interfacing. I don't know this part is the part of your course or not. So we will not cover the key pair interfacing for the time being. I will discuss with Dr. Mamatai, and then we will cover the key pair interfacing and the LCD interfacing. So 2 examples are still remaining in this chapter, which is key pair interfacing and LCD interfacing. I don't think so this should be the part of your course because there is no lab assigned to it. So these slides are for key pair interfacing, and the next slides are for the LCD interfacing. So there are only 2 modules left. First is the LCD interfacing. The next is a hard key pair interfacing. Key pair interfacing is same as segment interfacing. In 7 segment, we configured the pins as a digital output pins. In the case of keypad, we will configure multiple pins or parallel pins as a digital input pins. So those digital input pins will give us some data, and based on the data, we will check if the number that is pressed by the user, what is that number. So key pair interfacing and LCD interfacing might become a part of your course, but after the discussion with Dr. Tahir.
Excuse me, sir.
जी.
सर UART नहीं है कोर्स में?
UART भी है. UART आएगा आपके किस चैप्टर में? 9th चैप्टर आपका इंटरप्ट पर है, 10th चैप्टर आपका टाइमर्स पर है, 11th चैप्टर आपका UART पर है. 11th चैप्टर UART का है और 12th चैप्टर ADC का है. तो हम लोग ADC तक जाएंगे. ADC कॉन्फ़िगरेशन, UART कॉन्फ़िगरेशन, SPI, I2C कॉन्फ़िगरेशंस और टाइमर कॉन्फ़िगरेशन, ये सब कुछ हम करेंगे विद द एक्सटेंशंस ऑफ इंटरप्ट एज वेल. तो हर चीज हम इंटरप्ट की फॉर्म में भी करेंगे, पोलिंग की फॉर्म में भी करेंगे. तो UART will be the part of your chapter number 11 of your textbook.
सर जो LFI वाला प्रोजेक्ट है उसके बारे में वो क्या होगा उसका?
कौन सा प्रोजेक्ट?
सर जो कंबाइंड प्रोजेक्ट था कंट्रोल और MPS
उसके बारे में भी अभी तक जो है वो कोई डिसीजन नहीं हुआ. मैंने सारी ने आपके साथ कुछ चीजें शेयर, ग्रुप्स वगैरह बनाने की कुछ बातें शेयर की होंगी क्योंकि उन्होंने मीटिंग की थी हमारे साथ. अब देखते हैं क्या हो सकता है, कंट्रोल लैब कैसे चलेगी और MPS लैब कैसे चलेगी, बिकॉज दोनों के लिए अब हार्डवेयर रिक्वायर्ड है. तो हमने यही सोचा हुआ था कि मिड से पहले अगर हम असेंबली कवर कर लेते हैं तो मिड्स के बाद जैसे ही आप आएंगे आपको हार्डवेयर असाइन कर देंगे. लेकिन अब मिड के बाद भी आप नहीं आ रहे तो आप देखते हैं क्या हो सकता है.
सर लेकिन जो यूनिवर्सिटी ओपन होगी उसके बाद फाइनल्स और मिड्स के दरमियान एक मंथ का गैप है, तो क्या उसमें मतलब ऐसा पॉसिबिलिटी है कि हम हार्डवेयर पे काम करेंगे या
मेरा ख्याल है
बिल्कुल
कि
भी
आप
नहीं?
मेरा ख्याल है कि आप करेंगे, क्योंकि अगर जैसे ही 4 वीक्स के बाद यूनिवर्सिटी ओपन हो जाती है ना, तो हम लोग सारे एक्सपेरिमेंट डबल पेस पे करेंगे, क्योंकि जब तक आप हार्डवेयर नहीं यूज करेंगे ना, आप फाइनल ईयर प्रोजेक्ट नहीं कर सकते। ये वो कोर्स है जो आपके फाइनल ईयर प्रोजेक्ट्स को डील करेगा। अगर आप इस कोर्स में एफिशिएंटली परफॉर्म नहीं कर पाते, इट मींस आपका एफवाईपी अच्छी क्वालिटी का नहीं हो सकता। जब तक आप एम्बेडेड प्रोग्रामिंग नहीं सीखेंगे, आप अपना एफवाईपी स्टार्ट नहीं कर सकते।
और सर एक और बात, अगर हम जो मतलब सीनियर्स जो प्रोजेक्ट बनाते थे ये कंबाइंड प्रोजेक्ट LFR का, तो उनको